be talking about the transition metals in the fourth energy level, so N equals 4. But because it's in the D block, we're going to be talking about the 3D elements, so scandium all the way over to zinc. There's a couple of really unique things that happen that I'm going to show you. The first thing I'm going to ask you to do is copy this down in its entirety. So pause the video, copy this down, and then when you're done, restart the video. The first element in the D block is going to be scandium, and you notice how I have these written a little backwards. So instead of putting 4s2 3d1, I have 3d1 4s2, and the reason why is because the D block electrons actually go ahead of the S block and the fourth energy level. So scandium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. That 3d is on the same plane as the 3p6 electrons, or in the same energy level, and so they actually come before the 4s electrons. So you can see here I have them all written a little backwards. So the first thing, scandium, this is its electron configuration. So here I have the D block, and then over here's the 4s 2 electrons. What happens is scandium can form a +3 cation charge. So it's able to give away 3 electrons in bonding. These 3 electrons all go at once. So scandium can take on a +3 charge. Titanium, the next element in the D block, is going to be a 3d2 4s2, and titanium can take on a +2, +3, and a +4 charge. So it can take on multiple charges. So something unique about the transition metals is they can do that. And the reason why they can take on multiple charges is because of this right here. So titanium, in order to take on its +2 charge, is going to give away its 4s2 electrons together. It is easier to give away 2 electrons at the same time, just like a group 2 metal, like calcium gives away its 2 electrons, magnesium gives away 2 electrons. Same thing for these elements. It's easier to give away both of its valence electrons, which are the 4s electrons, at the same time to take on the +2 charge. To take on the +3 charge, it can then give away its D block electron, and to take on the +4 charge, it can give away its second D block electron. Vanadium, 4s2 3d3, again, that 4s2, those are the valence electrons. Vanadium can take on +2, +3, +4, and a +5 charge. So this up here, we'll just keep tabs, +3. So again, to take on the +2 charge, it will give away its 2 valence electrons, the 4s2 electrons. To take on the +3, first D block, +4, second D block, +5, the third D block electron. So it'll give them away one at a time in order to take on different charges. Chromium's a little funky. You would expect chromium's electron configuration to be the 4s2 3d4 because that comes after vanadium. So that would look like this. So you have your 4s2 electrons over here, and then your 3d4s would be up, 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 up. So that's what you'd expect it to look like. That goes along with the trend. However, that's not what chromium's actual configuration looks like. It actually looks like this. It pulls an electron from the outer energy level, the 4s, to fill in that last lobe to end up with an electron configuration like this. It turns out it's more advantageous to fill each lobe halfway in the D block than it is to have a full valence S energy level. Than it is to have a full valence S orbital. So it pulls from the S to fill the D, and chromium can take on a lot of charges. It can take on a +1, +2, +3, +4, +5, and +6. So to take on the +1 charge, it's going to pull that 4s valence, +2, +3, +4, +5, and +6. So lots of charges on that one. Manganese can can take on even more charges. It can take on +2, 3, 4, 5, 6, and a +7. Again, start with your +2, +3, +4, +5, +6, +7. So it can pull individual elements from the D block to get to different charges. Iron, you notice that after manganese, you start to see the backfill on the D block. So iron isn't able to take on as many charges as manganese because this right here is actually more stable in the D block when you have paired electrons than not. So it's not going to want to mess with those electrons. So you can take on a +2, +3, +4, +5, +6, and that's going to come from your +2 from your 4s2 electrons, +3, +4, +5, +6. Again, it's not going to want to mess with these two electrons because they are more stable paired together than these unpaired electrons. Cobalt can take on +2, +3, +4, and +5. So again, pull your first two electrons. So that's your +2, +3, +4, +5. Again, it's not going to mess with these paired D block electrons. Nickel's pretty straightforward. So you have your +2, +3, +4 charges. Not going to mess with these. Those are all paired. Not going to do anything about that. Copper is a little funky, just like chromium. So you would expect to see copper 4s2, 3d9. So here's your 4s2 electrons, and then your 3d9 is going to look like this. So just like chromium, what's going to happen is it's going to pull an electron from the s orbital to fill in that D block. That way it has a full D block, 3d10, which is way more stable than a 3d9. So by filling all the D block and then you have one electron in the s block, it's more stable. The weird thing is though, copper can actually take on a +1, +2, +3 charge. And so even though that last orbital is more stable, it can pull the 4s1 for the +1 charge, and then it's going to pull for a +2 charge, pull for a +3 charge. So it becomes more stable, but then it can give away those electrons anyways. It's kind of a strange element. And then zinc only takes on a +2 charge, and that's going to pull the 4s2 electrons, which are the valence electrons.